Well, hello everyone, and welcome to the next webinar in various webinar series. Today we're going to be talking about high rate testing of adhesives and composites. So my name is Scott Grindy. I'm a lead engineer here at Verist. But before we get started with the detail, with kind of the content of today's webinar, just like to talk a little bit, do some housekeeping up front. So generally speaking, for best results, please closing other programs on your desktop. If you'd like to ask a question during the class, I'd suggest using the chat feature. I think that the best way to do that is to type it into the chat box. I think unlikely I'll stop during the presentation just because I'm not very good at that, quite frankly. But then we can go back at the end. So if you want to ask a question, I would suggest you say something about, on slide 15, something, something. You ask a question. That way, it'll make it easy for me at the end to go back to where we were during the presentation. And then the last note is that the class is currently being recorded. And also, if you run into any tech support kind of issues, have trouble seeing things, just emailing Dory, Dory Mock, whose email is at the bottom of the screen here, and Dory will be able to help you out. So here's the agenda for our webinar today. So we're going to start with a brief introduction to Verist Engineering, and then we'll go through the kind of the background in terms of kind of what you need to know to understand kind of the rest of the webinar. And we're going to talk about kind of high rate testing of adhesives in two different ways. One of just kind of bulk adhesive materials, and the other way about adhesive joints kind of together. And lastly, if we get any questions during the presentation, we'll circle back on that. So I think we're going to shoot for about 45 minutes for the presentation today, and then we will do the Q&A at the end. So just a kind of brief introduction, Verist Engineering, we're a consulting firm located just outside of Boston. We provide consulting services, kind of what we like to say is at the interface of technology and manufacturing. And we focus on helping clients solve complicated problems using fundamental engineering principles. And generally speaking, we test and model polymers daily for advanced finite element simulations, which is kind of the core and the motivation behind our presentation today. My background is that I have a PhD in material science and engineering from MIT. Generally speaking, I work with advanced polymer characterization, mechanical testing, adhesive joint design, materials chemistry, and materials selection. A little bit more about Verist. We kind of think of ourselves as having kind of three rough areas of expertise. One in engineering simulation, so that can be any type of engineering simulation, structural mechanics, fluid dynamics, heat transfer, electromagnetism, electrochemistry, other types of chemical reactions, and also what we like to call kind of multi-physics simulation, which is where kind of more than one of those types of physics is kind of involved, and they need to talk to each other, they need to kind of communicate with each other. So they think about like a structural thermal analysis, for example. Kind of the middle vertical, which is a little bit more kind of relevant to what we're talking about today, is this material testing and modeling, where we have both kind of conventional as well as some custom built test equipment, which you'll hear about much later in the presentation. We talk about kind of some of the custom test methods that we've developed for advanced adhesive characterization, especially at high rates or impact rates, is just what the focus of our webinar is today. And the last kind of business area for us is failure analysis. So this is usually something broke and we don't quite understand why, so we kind of take a rigorous approach to kind of moving through looking at the failed parts, whatever they are, and trying to figure out where did this part start to break, what caused it to start to break, and then the next step is, of course, how do we prevent this from failing in the future? So, just at a glance, Verist, we're in Needham, Massachusetts. We're not that old, founded in 2006, but right now we have 15 staff, most of us with PhDs, backgrounds mostly in mechanical engineering and material science. Generally speaking, we like using fundamental engineering science to solve industrial problems. And then that last bullet there is kind of our little catchphrase, which is academic expertise applied on an industrial time frame. Now, here's just another kind of highlights of our modeling and simulation expertise: solid mechanics, fluid mechanics, electromagnetics, and multi-physics. And we are pretty software agnostic. We tend to use Abacus, COMSOL, ANSYS, and a little bit of LS-DYNA, just generally speaking, depending on the needs of the problem at hand. So we're not kind of constrained into one kind of particular software package. We'll pick the one that has the availability and the tools to solve the problem at hand. Um, in our mechanical testing lab, we do have what I would call conventional load frames to do things like tension, compression, and shear, as well as kind of the impact rate, tension, and compression on our custom test equipment. Fracture toughness, obviously, a very of interest to the audience today, as well as dynamic mechanical analysis and a little bit of kind of cyclic loading. We also regularly do what we call validation tests, which are usually kind of more complicated test geometries than kind of conventional tests. That's ball impact or punch testing, as well as what we call custom validation structures, which are usually just designed to test a product, something that's been produced, and we will kind of design a test fixture around loading the product in a particular way to kind of make sure that the work we've done to make sure that the simulation material models are so complicated are accurate. We use a lot of digital image correlation and high-speed video, which you will obviously hear more about later in the presentation today. So let's move on to kind of the background knowledge here, which is what I'm calling analysis and simulation of adhesive joints. I like to start this section with a question, which is what makes predicting joint mechanical behavior hard? And the kind of the important things are that the joint strength depends not just on the adhesive properties itself, but also the geometry of the problems, the bond line thickness, the adherence, the materials that are being bonded together, as well as the geometry of the joint. The problem with this is that many adhesive suppliers give you a data sheet that sometimes describes the material performance with adjectives and not material properties. So you see things like high strength or outstanding environmental performance or excellent toughness. And these are perhaps good descriptors or accurate descriptors of the material, but it's not something that we can use to analyze the joint in our product that employs this adhesive. And finally, typically the data, any quantitative data that's supplied about the adhesive will be on a few joint geometries for comparative purposes, things like lap shear strength or peel strength, things like that. But that, as kind of we'll discuss later, these aren't always relevant to the stress states from these tests are not always relevant or representative of the product at hand. So it becomes difficult to actually predict how well your product is going to survive based on the data provided in the data sheet alone. And so when we think about FEA, we think about there being kind of three groups of inputs. One is the geometry, essentially your CAD of how the parts fit together. The second part is the boundary conditions, which is how are the kind of loads applied to this part. And the third part is the material model, and that's kind of what we're going to be focused in on today, which is how are the mechanical properties, the performance of the adhesive represented numerically within the finite element software. And we're going to talk a little bit about both cohesive zone models and continuum material models, which are kind of the ways that we like to think about adhesive material modeling. So there's kind of two different approaches for simulation of adhesive joints that have some trade-offs. There's not really one of them is not better than the other. It's really about kind of deciding which one is more useful for solving the problem at hand or answering the question at hand. So on the left, I'm showing you cohesive zone modeling. This is based on what are called traction and separation laws. We'll talk a little bit more about those later. But the kind of the key point about a cohesive zone model is that it's designed to capture adhesive failure. So during the simulation, adhesive starts to fail, and that changes the stress distribution on other components. And that's what you're kind of considering, or that's an important outcome for the simulation. We'd be more likely to recommend a cohesive zone model approach. Kind of the drawback of a CCM approach is that it doesn't resolve the stress variation through the thickness, and it doesn't really capture time-dependent behavior very well. But the trade-off for that is a cohesive zone model is much more computationally efficient than a continuum material model. So if you have a very large assembly with a lot of things going on, it takes a long time to get that simulation to converge. You'd be more likely to recommend a cohesive zone model because we're going to kind of trade off some of the accurate description of the physics for kind of efficiencies in computational speed. Now, to kind of compare with that is continuum material modeling. And so these are, generally speaking, more detailed constitutive models. They're not, generally speaking, not very good at modeling failure, or at the very least, it's more difficult to model failure. with a continuum material model, and they are much more computationally expensive. So you're getting more detail. You're resolving the stress essentially through the thickness of the adhesive joint in this particular case. But you're kind of paying for that on the back end, which is that you need to spend more time on your computer. It's going to take longer to run. It's going to take longer to converge. Okay, so that's kind of the background for what we're going to talk about kind of later. So let's talk about high rate testing of adhesive materials. So this is kind of focused around continuum material models, and it's how do we characterize those adhesive materials at high rates. But first, we're going to talk a little bit about, why do we need to be concerned about the strain rate when we're doing a mechanical test of an adhesive? And it's because adhesives are polymers, and polymers are rate dependent. So what I'm showing on the screen here is an engineering stress, engineering strain curve of the same polymer, but tested at 3 different strain rates. So 0.004 strain per second, 0.4 strain per second, and 200 strain per second. You can see that this kind of apparent strength of the material changes from about 42 megapascals all the way up to about 63, let's say, megapascals as we go from what I would call a quasi-static rate to a moderate rate all the way up to kind of an impact rate. And so if you aren't able to kind of test your material at these impact rates, it's you're not going to be able to kind of forecast how your part is going to respond under high strain rate or impact conditions. I think especially for this material, the strain to failure decreases by a lot as we go from low rates up to high rates. And so that may be relevant for your application. You may have a material that fails under impact, but doesn't fail at all at kind of quasi-static conditions, kind of based on these differences in behavior. So that can really kind of reflect how we might think about changing the design to accommodate this kind of expected behavior for a material. And so how do we actually do these types of tests to get these kind of continuum material models that we use in finite element simulations? And so typically we're looking at data collected on bulk adhesive specimens. So things like tension, compression, maybe some shear, you can see up in the right corner over here, as well as a DMA or dynamic mechanical analysis. And so the kind of key and perhaps most important part of a well-calibrated continuum model for a bulk adhesive is getting test data at strain rates and at temperatures that are relevant to the product's kind of expected use conditions, because that's how we can actually calibrate a material model that's accurate for the material under those kind of expected application conditions. So before we even start doing any testing at all, that's kind of the first question we'll ask clients when we start projects like this is, what are the expected loads? What are the expected strain rates? What's the temperature window that's relevant, because we know we need to test the material kind of over that range of temperatures. So how we might do some impact rate testing, what we use for this is actually a custom test frame that we developed. We call the drop tower. And so this test frame has a capability of hitting strain rates of about 1,000 per second in tension or about 2,000 per second in compression. So the way this works is we have this impact sled. We kind of bring this up to a kind of a fixed height. And then at the start of the test, there's a kind of release that drops all this weight. The specimen is down here in a fixture that allows it to be loaded in tension, which is what you can see in this video here. We'll also do compression, shear, or even kind of custom test fixtures just based on client needs. But importantly, we're going to use high-speed video to analyze these tests. And so that's something that is especially important under impact and high strain rates, because it's very much more difficult to kind of instrument the sample using kind of conventional extensometer sensors, for example. I'll just play that one more time. This is a video that's taken at 80,000 frames a second. So this probably lasts 1 millisecond, give or take, as you can see from this video. And so using high-speed video to capture the test and then analyzing the high-speed video after the test is in our experience the best way to measure the impact properties of polymers and adhesives at high strain rates. And so how do we take that video and actually turn it into useful information? We use what's called digital image correlation. So you can see even on the previous slide that we applied this kind of black and white what's called a speckle pattern to the surface of the sample. So it's basically a series of high contrast points that digital image correlation software can use to calculate the strain field across the entire specimen in a non-contact manner. And so this is really important to us for reasons like this, where there's for this sample in this image, excuse me one second, where we've got some necking occurring, so it's kind of a local spot where the strain locally is much higher than it is at other points on the sample. And it also allows us to be much more flexible in how we run these tests in terms of test geometry. So this is a shear test, so we're able to calculate the shear strain using this video-based technique, or this kind of notch tension test, where you can see quite nicely the kind of the strain concentration in this necked or kind of a notch region. Excuse me. Now, for some samples, the drop tower is essentially much too big of a hammer, so to speak. So we developed what we call the thin film test machine, and so this is a similar principle, but it's designed to work with thin films and very soft materials, things like pressure-sensitive adhesives, foams, optically clear adhesives or OCAs, and kind of thin elastomer films, with thicknesses on the scale of microns, so down to about 50 microns. I'd say up to a few hundred microns is typically what we will use this fixture for. And so you can see this down here, and it has a similar principle, except that instead of using gravity to drop all the weight on the specimen, we're using a pneumatic striker that uses compressed air and then a release, and it kind of sends a pressure wave through the specimen. And this fixture right here is kind of set up for compression. So the specimen would be mounted right here, and this platen would come down and compress the sample. And so there's a load cell, kind of impact rate load cell underneath the sample, as well as this displacement sensor that basically tells us the position of the platen. And that's how we calculate the stress and the strain in the sample. We also have fixtures for this to test these types of materials in tension or compression. Just to look at an example of what some of these test results look like, this is a urethane foam tape that's kind of used as an energy absorber. So here's the kind of the macro stress and strain, but looking kind of at it much more closely at kind of the lower strain regime, you see that even at 80 per second, 80 strain per second is a relatively high strain rate, but there's still some strain rate sensitivity moving up from there up to around 1700 strain per second. And so this kind of behavior is what we expect from elastomer foams like this particular kind of foam PSA tape, where we get this kind of stress plateau with some compaction at very, very high strains. But this this plateau level is extremely strain rate sensitive, even at something I would still already consider to be a high strain rate. So it is really important to measure the behavior of these materials at multiple high strain rates. And so this slide is just showing kind of once we have collected all of this test data, how do we turn that into an actual material model that we can use in our simulations? And so we don't in some of our other webinars we talk about this in a little bit more detail, but the generally speaking, the way it works is we collect this as time, stress, and strain data. The advanced continuum material models that are useful and relevant for most adhesives and other polymers are relatively complicated. So we're not doing something where we're just measuring the modulus, measuring the strength, and then kind of putting those values into ANSYS, Abacus, or COMSOL. What we're doing is kind of solving the differential equation that maps kind of the stress, strain, and strain rate and time-dependent behavior of these materials through a program that's called mCalibration. And once we do that, once we've calibrated all of these material parameters, we then export that into what's called a material card that is an input for the kind of engineering simulation software that you're using. And so usually when we do projects like this, that's kind of the final deliverable that we hand to the client. Fundamentally, it's a text file, but it's a text file that that's kind of formatted for the particular engineering simulation software, and contains all of those kind of calibrated material parameters to describe the strain rate dependence or temperature dependence and kind of other nonlinear behavior that we expect from polymers, plastics, and adhesives. All right. So moving into kind of the final section, we're going to spend a fair amount more time on than the other sections. We're going to talk about high rate testing of adhesive joints. So this is once we're beyond the bulk material characterization, we need to consider these materials as joints, we need to consider the adherence quite specifically. So before I talked a little bit about the distinction between cohesive zone modeling and continuum material modeling. When we're modeling joints, we'll typically, that's the kind of the mental framework that we use to describe cohesive zone modeling, which is that we need to test these materials as joints, not just as bulk materials. And so cohesive zone modeling is very good. It's kind of designed for that purpose. And what we're going to be looking at is trying to determine what's called the traction separation law. So the traction, that's the kind of the surface traction. You can think of it as the kind of basically the stress on the surface of between the adhesive and the adherent, and the separation, which is just the change in separation between the two adherents. So the separation could be normal, which is kind of shown in this figure, or shear, where this top adherent would be moving kind of to the left or the right, as kind of drawn on this figure. And so in order to actually calibrate a cohesive zone model for these materials, we need to start by measuring the traction separation law, because that's kind of the input that goes into a cohesive zone model. And you think about these traction separation laws, they do resemble kind of stress strain curves, right? The traction is kind of analogous to the stress, in a bulk materials test, and the separation is kind of analogous to the strain. So you can think about these as being related to kind of conventional materials parameters, like the modulus. We tell it, is related to the kind of the stiffness of this initial section. The strength is going to be related to the maximum stress here. The fracture toughness, that's going to be the area under the curve. And the strain to failure is going to be analogous to, it's called delta C, or the kind of the critical separation, basically as far apart as I can pull these adherents before they fail. The problem is, you could just take these values and kind of plug them in a CZM, and you might do okay, but there are pretty significant differences in the stress state between a bulk specimen and an adhesive joint. So these properties will, I would say, never match exactly, and it's very hard to predict in our experience. So that means that, again, the technical data sheet values aren't really going to be valuable as input. And the other thing that I wanted to mention before we go any further is that the way that cohesive zone models are implemented in different commercial FEA codes can limit how you analyze your materials. So of the kind of main programs that we use, they have different kind of levels of kind of sophistication in how they actually input cohesive zone models. So you can think of a bilinear or an exponential or a trilinear, or some of them even have kind of table lookup type models where you can put in kind of any arbitrary shape. But the important thing to remember is that depending on which software you're using, it can limit how you're analyzing the material, and that different versions of cohesive zone models are being released with each kind of new annual or biannual release of these software. So if you would like a different one of these to be implemented in the software that you use, I would suggest sending an email to the kind of the relevant application engineer at those companies, and requesting those features, because that can be limiting in terms of how we can actually do simulations of these adhesive joints. But going back to the traction separation laws that we need to measure to calibrate these cohesive zone models, we have to measure the traction separation law for each adhesive, bond line thickness, loading rate, and temperature. The best, or the kind of useful property of traction separation laws is that they are the derivative of what's called the J integral with respect to the separation. So the J integral is a path-dependent integral that goes kind of around a crack tip. It's a measure of the strain energy release rate of a particular adhesive joint and loading configuration. But the most useful property for us is that the J integral and the separation delta are both measurable with digital image correlation. We'll talk a little bit more about that on the next slide. So that means that in order to get this traction separation law, what we're actually going to do is measure the J integral as well as separation, take the derivative of J with respect to the separation, and that's going to give us the traction. So these are the kind of the two common adhesive specimens that we test, especially for structural adhesives at low rates, at quasi-static rates. So the one on top, this is a double cantilever beam. This is a mode 1 or kind of peel pure peel test for the structural adhesive. So we take two typically aluminum or steel beams, although you can use other materials if you're more careful, and kind of pull them apart some distance away from the crack tip. So basically there's an adhesive joint between these two beams kind of towards the right, and we can measure the rotation, basically this opening angle of the two adherents, as well as the load, and we know, of course, the geometry of the specimen. We can calculate J. So this is how we run kind of a mode 1 test. In mode 2, or shear, we use an end-notch flexure test. So there's also two beams that are kind of bonded together. You can see the adhesive joint stops right about here. This is where our crack tip is, and we load this kind of as you would load a 3-point bend specimen. And so what this does is it puts the crack tip of the adhesive in almost pure shear. And then we have this expression where we measure the rotation, again, the rotation angle of the beams at each of the supports, and use this expression to calculate the J integral for the test. And then we can then translate that back into the traction. But I want to focus today more on the high rate testing aspect of things. So those are the tests that we use at quasi-static rates. But as we've been discussing, adhesives can have substantially different toughness at high strain rates. And so the idea is that I can't tell you right now if adhesive or adhesive joint X, aluminum and epoxy XYZ is going to be tougher at impact strain rates. It's going to be weaker at high strain rates than it is at quasi-static rates, or it's going to be the same. It's just something that, in my opinion, you're better off just testing rather than trying to forecast that. So the nice thing about the end-notch flexure, that mode 2 test, and the single leg bending, which is a mixed mode test that we normally run for these types of test programs, those are very straightforward to perform on high-speed load frames like our drop tower. However, the double cantilever beam, or that mode 1 test, is practically limited to lower strain rates, and just due to the geometry of the test specimen. That's because the opening speed of where the load is applied is much higher than the actual strain rate at the crack tip, because you have these lever arms of the DCB specimen. So the kind of fundamental challenge that we pose to ourselves is how do we measure the mode 1 toughness at high strain rates, given that we really fundamentally can't use the double cantilever beam specimen that we use at low rates. And so we looked through kind of what's available for kind of already known or standard tests for impact peel strength of structural adhesives. And this particular ISO standard, the wedge impact peel test, uses a kind of an impact frame, much like our drop tower, to drive a wedge between two bonded adhesives. And so this, we thought about this and said, okay, so this is an impact rate, mechanical characterization of this structural adhesive joint. The problems with this test are that you end up with a lot of plastic deformation of the adherents, and that means that when you're measuring the kind of load displacement relationship during these tests, you're not actually measuring the toughness of the adhesive joint. You're measuring kind of the performance of the adherents as well as the adhesive joint. So there's basically a lot of different sources of energy energy dissipation for the kind of mechanical loading, and it's impossible to differentiate between what's deformation of the adherents and what's actually what energy is being dissipated by the adhesive joint itself. So we took this test and kind of combined it with our double cantilever beam, our low rate double cantilever beam test, to design what we call the wedge loaded double cantilever beam. So this looks conceptually very similar to the wedge impact peel test, but it has the distinct difference of using substrates that do not deform plastically during the test. So we don't have that source of energy dissipation, as well as, because we are using high-speed video to analyze these tests, we can actually calculate the J integral during these tests, as well as measure the separation, much like we do in our low rate tests. And so because we can perform this test on our drop tower, it gives us a way of measuring the mode 1 traction separation behavior of structural adhesive joints at high rates. So just in particular, this is an epoxy, I believe, steel joint. And this video is taking about 15 milliseconds, kind of start to finish. So we use the velocity of the wedge kind of from right to left is about 5 meters per second in this particular example. So the question we have now is, we can run this test. How do we actually use this to calculate the toughness? And so if you kind of look through the literature, you can find what's called the linear elastic fracture mechanics solution for a wedge-loaded system like this. If you're familiar with something called the Bowing wedge test, this is basically this is what this test looks like, except without any motion of the wedge kind of whatsoever. But what this calculation for the toughness, which here I'm calling G, requires is a measurement of the crack length, which is the kind of distance between where the adhesive is and where the wedge is. And so that's something I'll tell you is very difficult to do, even from very nice high-speed video. You get a lot of errors. There's a lot of kind of stuff happening around the crack tip. It's very difficult to instrument that or do it in an automated way that has the accuracy that we need, especially because you can see the crack length here, the letter A is raised to the power of 4. So that means that the error, your inaccuracy in the measurement of the crack length is also raised to the 4th power. So not only is it, I would say, the most difficult thing to measure during the test, it's also the kind of the measurement that's going to cause the most error in our calculation of the kind of the toughness of this joint. So we don't use this expression to calculate the toughness. We actually use a J integral approach. And so just going back to our double cantilever beam, our low rate double cantilever beam, you remember that we have this expression for the J integral that relies on a measurement of the load, kind of the load that's opening the two beams this way, as well as the opening angle theta of those two beams. And so we asked ourselves, can we kind of take this J integral expression and then apply it to the wedge-loaded DCB specimen, actually calculate the J integral without needing to measure the load and calculate the toughness without needing to measure the crack length. And so here's the kind of the solution for that. We basically treat each of these beams as a kind of simple cantilever beam, so that if we know the rotation angle of the beam in two different spots located some distance L apart, then we can actually calculate the load required to deform kind of a simple cantilever beam to those rotation angles. So we take that and we calculate the load using those two rotation angles and then plug that into our expression for J. And so now what we have is an expression for the J integral that doesn't require any direct measurement of the load. Remember, we're using the deflection, the kind of the rotation angles of these beams to calculate what the load is, or the effective load is that's applied at the wedge. We do not need to measure the crack length at all. We just need to know the distance between these 2 points where we're measuring the angles, which is something that we specify. So there's not even really any error there, relatively speaking. And of course, the rotation angles is also something that we measure with high-speed video. So kind of give a more holistic example of how this works. This is a composite specimen. This is a long fiber composite where there's a kind of a non-bonding insert that's inserted into the layup during the kind of the curing process. And so we actually drive a wedge through that non-bonding insert, which stops right about here. And the crack is going to propagate from right to left as we run these tests. And I'm going to step through this. We use a computer vision algorithm to measure a couple of things. The first one is the position of the wedge. You can see the little blue kind of plus sign where the wedge is. So we're going to keep track of that during the test. We're going to keep track of the approximate position of the crack tip. So not specifically the position of the crack tip to calculate the crack length. What we really want is a point that is somewhere, the way this test is set up, to the right of the crack tip to calculate the rotation angle. That is that kind of theta 2 parameter that goes into our expression for J. And we do that using kind of a computer vision algorithm that keeps track of the contours of the beam. So we know, excuse me, we know what the contours of the beam look like, then we can calculate the rotation angle, and we just need to calculate that basically in 2 spots, right at the wedge and kind of right down here. Excuse me. And as long as we know the distance between them, that's this letter L, then we can calculate the toughness during the test. And so as you watch this video play, you can see that the computer vision algorithm is kind of keeping track of all those things simultaneously and is allowing us to kind of measure the toughness of or calculate the J integral of the specimen kind of throughout the entire test, basically each high-speed video frame that we're capturing during this test. I think there's about 1,000 video frames. So we get about 1,000 data points from this particular setup of the test using a 20,000 frames per second video. So before we go any further, I do want to talk about kind of how we, a little bit of the detail in the computer vision algorithm and how we actually determine the location of the crack tip. And we use a process that's called template matching. So if you're going to look up in the kind of computer vision world, software is designed for computer vision. OpenCV particularly is kind of the package that we use. That's the kind of the phrase you want to look up to learn a little bit more about this procedure. But I've got this kind of toy example here that kind of illustrates the process that we're going to use to keep track of the crack tip during the test. So template matching is where you take a template image and then a kind of a candidate image, and what we're going to do is try and identify, in this particular example, all of the coins in the image. And so what happens kind of under the hood is that the software does a convolution of the template image with the candidate, kind of the test image, and finds the areas that have the kind of highest correlation between the template and the test image, and uses that, basically those kind of peaks of correlation, to identify all of the coins in the image. So this is kind of a fun and cute example. How do we actually apply this to our kind of wedge-loaded impact DCB specimen? And so what we're going to do is leverage the self-similar shape of the beams near the crack tip as the crack propagates during the test. So basically, as our template, we take our pre-test image and we select the area kind of near the crack tip. And we're going to use that as our template. Our target image, so this particular image is from about, I think it's about halfway through the video that I just showed you a few slides ago. And so we're using this as our template and basically say, where in our target image do the beams most look like kind of this, the area where the crack tip, there's a crack tip with two beams that are opening, the crack is open, and there the crack is closed. We're also going to do this, before we actually do the template matching procedure. We first pre-process the images to create a binary image. And I'm going to tell you that if you'd like to implement this algorithm or an algorithm like it, kind of in your own testing, this step is the one you should spend the most time. You will spend the most time on. It's probably the one you should spend the most time on, because this is where kind of you're going to do all the kind of the filtering and noise subtraction to make sure you basically get like high quality, good contrast, in this case binary image of your test specimen. And you'll notice that in this upper image, we've actually lost some detail going from the pre-processing step. So we have a crack tip that ends, I think, right about here in the template image. But if I look at my pre-processed template, it ends about here, and that's okay, right? Because we're not actually trying to measure the crack tip. What we actually want is, I like to call a conservative estimate of where the crack tip is. I want to make sure that the point that we're measuring is actually to the right of the crack tip. So again, basically the way we use this algorithm is that we actually target a spot that's about here, basically the center of this image, and that's where we're going to actually calculate the rotation angle of the beam a little bit to the right of the crack tip. And then as we kind of do that template matching procedure to calculate the correlation between this template and each kind of subset image of the target image, we identify the kind of the maximum correlation point, and that's where we actually identify the crack tip. Not exactly the crack tip, as we just discussed, our conservative estimate of where the crack tip is, but using that template matching procedure, that's how we actually track the approximate position of the crack during the test. So just to show you kind of more explicitly what this looks like, the video on the left is the one that we looked at before, that carbon fiber composite. The image on the right, this figure on the right, is showing the J integral, the mode 1 J integral, kind of during the test. You can see there's a couple of, basically this flat part is before the wedge actually starts moving, so the camera actually starts recording kind of a little bit before the impact event, basically the start of the test. And this value is actually very close to the low rate, the quasi-static toughness of this particular material. That's because as we drive the wedge, when we insert the wedge in the material, we basically start with a J integral because the cantilever beams are actually loaded at the start of the test. But the kind of steady state, or the kind of the impact rate toughness of this material is actually a little bit higher than its low rate toughness. We're going from somewhere that's about say 0.37 or so up to kind of an average of about 0.5. And in fact, there's kind of a stick slip like behavior going on here, which you can see kind of both in our calculation of the J integral, as well as if you are kind of looking at the kind of our estimate of the position of the crack tip during the test. So you kind of have a peak fracture toughness around 0.65 or so, and then this crack arrest toughness of about 0.45. So it's this, using high-speed video in this way gives us much more information about how these specimens actually fracture and how the crack propagates during the test than it would from kind of more conventional test methods. Moving on to kind of a structural adhesive application, we use a second camera, which I'm not showing the exact area of, but kind of zoom it in closer to that crack tip, and much like we do for the kind of low rate quasi-static adhesive testing, we can calculate we can measure the separation. So now we're measuring both the J integral during the test, you can see here, as well as the separation during the test, which you can see here in the lower figure, and use that to measure the traction separation law, which you can see here. So the J integral as a function of separation is shown in blue, and then our fitted kind of traction separation law that can go into a cohesive zone model is shown in black. So finally, kind of putting it all together, we can take the traction separation law that we measure during our impact wedge test. We can put that in with our mixed mode and mode 2 traction separation laws and combine them into a cohesive zone model that we can then use in a finite element simulation to kind of, in this case, this is a battery pack that's undergoing impact with a hard surface. And now we can actually kind of interrogate the internal structure of this battery pack and perhaps recommend some design changes to our client. So that wraps up the content today. We'll see if there are any questions. I don't think I see any in the chat. No, I do not see any questions, but I say thank you everyone for attending today, and I hope we'll get the chance to work with you again soon. Before we get out of here, I do want to plug our upcoming classes and webinars. We're talking next month about interface mechanics, and then a little bit more about polymer testing for FEA and CAE. We also do have some paid webinars and classes kind of upcoming, focused around testing and modeling the polymers for finite element simulation, as well as an in-person class at our facility here in the Boston area in May. So if you're interested in those, you can check out our website. You can find them there, or send an email to this contact@verus.com, or to me, sgrindy@verus.com. We'll happily give you more information that you're interested about those classes. Thank you so much.